After univariate regression, we do multivariate regression. The basic idea is perfectly simple. We just add more x variables into our code. Sure, the math gets a little complicated, which is why it's sort of segregated in the curriculum. But in this course, we've left off most of the math calculations, leaving it at the computer to muck around with. In the formula, we're going from y equals beta naught plus beta 1 times x1 to y equals beta naught plus beta 1 x1 plus beta 2 times x2 plus on and on to beta k times xk. We're just adding a bunch of subscripts. And when we write the code in R, instead of lmy twiddle x1, we use lmy twiddle x1 plus x2 plus x3. Just go crazy with it. There are a few details to keep track of. For instance, when we're doing hypothesis testing on each coefficient, the t-test is going to have n minus k degrees of freedom, where n is the number of observations, k is the number of variables in the regression. If we have relatively few observations, which is common when we're doing macro, then we need to be careful about how many variables in our regression. But in other cases, we might have thousands of observations. So, like these little labs we're doing in class with census. We have enough observations, we can add a lot of additional x variables. Multivariate regressions, we still interpret the coefficients as the slope. But it's how much the average value of y would change when that one particular x variable changes, but all the others are held constant. If you remember your multivariate calculus, that's just saying the coefficient estimates the partial derivative. The beta estimate is partial y partial x. Also from multivariate calculus, you might remember that at least locally, any continuous differentiable function can be approximated as a linear function. So while it may seem that our assumption of linearity is quite stringent, on the other hand, you can make a case that it's certainly going to be true for a pretty generic class of functions within at least a local area. Often we include dummy variables among the x. Dummy variables are either 0 or 1. The coefficient on the dummy variable is the change when that dummy variable goes from 0 to 1. In R or other statistical packages, they report the coefficient estimates, the standard error of each coefficient estimate, the t-stat, which is the ratio of the coefficient to the standard error, and the p-value, the area of both tails with that degrees of freedom, n minus k, calculated from the t-statistic. You should be able to understand where all the computer is getting those. It's not sorcery, it's just math. Some notation details. The model fits y to be beta naught plus beta 1 x1 plus beta 2 x2, so forth, plus e, the error. The fitted values are going to be denoted y hat, calculated from the estimated coefficients. Each gets a hat notation. Beta naught hat 1, beta naught hat, beta 1 hat, etc. The residuals are what's left over. We subtract y minus y hat, which is the same as y minus each estimated coefficient times the true x value. As with the univariate case, the mean of the errors is going to be 0, because that's how the intercept term is defined. Here's a simple example using CEX data, consumer expenditure data. The model is the classic Engel study, looking at what fraction of income do households spend on food. If you remember back in micro, you studied the Engel curve for individual consumption choices. Some of this coding uses the package AER. The y variable is a fraction of income spent on food. We'll model that influence by the personal age, size of the family, whether the person is female, whether the person is African American, Asian, other race, American, Indian, Native American, Hispanic, educational qualifications, which means dummies for whether they have a high school degree, whether they have some college, associate's degree, bachelor's degree, or an advanced degree. This is the results that R is going to spit out. We look down those coefficient terms where each line displays the coefficient estimate, its standard error, the t-stat, and the p-value. The first line is the intercept term, which we usually ignore as a nuisance term. Each term gets stars if the p-value is low, because that indicates the coefficient is likely different from 0 if all the assumptions are correct. In this model, the age of the reference person has a negative estimated value, and it is statistically significant, which would imply that older people spend a lower fraction of their income on food. Family size is perhaps surprisingly not strongly related to the fraction of household income spent on food. Perhaps as people's family size go up, their income and food expenditure both tend to rise in rough proportion. You can go through the rest of these coefficient estimates. We'll talk about them in class a great deal and we work through it. With all these educational qualifications, those are all measured relative to somebody who has none of those, who doesn't even have a high school diploma. All the coefficients are negative, which we would probably interpret as showing that food expenditures are a smaller fraction of income as people get more income. Food might be something of an inferior good. People with lower income tend to spend a higher fraction of that income on food. In R, we have lots of handy ways to work with the output from the LM call. Once you estimate the model, as I did on the previous slide, you can access different segments of the model. The coefficients of model angle brings the coefficients. Fitted value of model angle brings the fitted values. The residuals, which are the differences of y hat from y, the confidence interval gives the confidence intervals for each of those coefficients. The plot gives a whole bunch of interesting plots. ANOVA will give you the ANOVA tables. You get the idea. You can generate predicted values for particular cases as well. We might want to ask, what is the predicted proportion of income spent by a household where the reference person is age 30, family size is 1, female equals 1, African American equals 1, the other race ethnicity values are 0, person has a bachelor's degree, and R will tell me what is the predicted value of Y in that case. It's often a good way of assessing if the model seems reasonable. It's also a way to generate counterfactuals. For instance, if I want to know how much wage variation would remain if I took out age effects, i.e. by setting everybody's age to be 35 or something. Note that R distinguishes between confidence intervals and prediction intervals. If the value that I'm trying to predict is within the observed X, then I'd use the confidence interval, while if the prediction is outside that interval, then it's a prediction. That's important for time series, like trying to decide the interval for a prediction of GDP next year or something like that. It's less relevant for the micro data that we're going to be using mostly.